Hi boys, this will be our last lesson on the Extension 1 course. Might tidy up some details or clarify some concepts, but this is the last exercise for the last topic. It's called sample proportions. The crux of this is that if you take enough samples for a discrete random variable, we can approximate that with a continuous model, and then we can use the z-score table. So let's have a look. A population proportion P is the number of people or objects in the population that have a certain characteristic as a fraction of the total population. Okay, so for example, if we have 2,745 seagulls in a population of 9,232 living on the Central Coast, they have red eyes, and the population proportion is given by this. Okay. Now, this is called a population proportion because we have the whole population into consideration, and we know how many of those seagulls have red eyes. So this is the proportion of red-eyed seagulls for the whole population. So that's a fairly basic idea. Now, trouble is, when the population is large, it makes it logistically more difficult to find out the total population or to even count the total population, to survey the total population. Imagine doing that for all of Australia. That's a big job. So when the population is large, we usually take a large sample from the population and assume that the sample proportion is a good estimate of the population proportion. Now, your sample, when you take it from the main population, so if I just come down here, so this is P with a little hat on top of it. Just imagine P is the whole population. So what you're doing is taking a sample of the population. And that's the symbol we use for that P with a little hat. Now your sample should be representative of the whole population. So that means, let's just say you had 50% males and 50% females in your population. That means your sample should also have 50% males and 50% females. So the sample should be representative of the characteristics of the whole population. That's important to mention. Okay. Now, as long as we've got a good representative sample, we can say the sample proportion is a good estimate of the population proportion. Okay. So in an ideal world, we'd always have the population proportion because that'll give us the most accurate answer, but we've got to take samples, and so we use the sample proportion. Now, there is a nice little formula for sample proportion, very similar to this. Is x over n. X is the value of your binomial random variable x with the probability of success p and sample size n. Okay, so n is your sample size and x is the value of your binomial random variable. Okay, so in this case, for the population proportion, our binomial random variable value was 2,745. Okay, now the value of p hat, of your sample proportion, will be different for each sample. So here's one sample, I can take another sample, but every time I take a sample, I should be getting something slightly different. Right, different numbers involved. Now let me just get there you go, it's better. So if I take another sample, there we go, and the symbol is P with a little hat on the top. So that sample will be different to this sample. Okay, so each time I do my sample and I use my formula to calculate what P hat is, remember n is the sample size, then my values will be slightly different. Okay, now these sample proportions I'm finding, so if I find another one as well, let's just say I did 3 samples, but obviously I've got to take more than that to get a good idea of what's happening. Okay. Now, these sample proportions form a discrete probability distribution called the sampling distribution of proportions. All right, so this is a discrete random variable we're talking about. Okay, so first example, nice easy one. A company produces batteries and does annual checks to see what proportion of them are defective. In the last 3 years, the number of defective batteries were as follows. So we have year one, 31 defective out of 1,500, year two, 19 defective, etc. Now we've got to find the sample proportion for this. Now this is not population proportion, this is sample proportion, and these represent samples. So if you look at the first one, the sample proportion, so let's just use the correct notation, p hat, that is 31 out of 1,500. Okay, well you've got to convert that to a percentage. So type that into your calculator. You should get about 2%. In fact, it should be to one decimal place 2.1%. Okay, let's have a look at another one. Year two, 19 defective. So 19 is the value of my random variable. So remember, my formula is x divided by n. So 19 is the value for the random variable, and n is my sample size. So it's going to be on 1,100. Right? And whoops, should have a little time sign there to convert that to a percentage. And that should give you 1.7%. Last of all, p hat will be 45 over 2,000. Now to convert that to a percentage, times by 100. Now you will get 2.25% exactly there. Now, that's the sample proportion. Part B says use these results to state an average percentage of defective batteries for this company. So using these results, we're just going to have 2.1%, find the average, 1.7% plus 2.25%. Okay, and that will be all divided by 3 to find the average. And you should get for those numbers 2.02%. Okay, so that's the average percentage of defective batteries. Okay, so let's move on. Now, sample size and the normal distribution. Let's have a look at this. This is where we start to get into the more important ideas. Now, we can use the binomial distribution to explore the sampling distribution of proportions using different values of p and n. Okay, since the calculations become more difficult with larger sample sizes, we can use technology to help draw graphs of sample distributions. Now, there's not much to do here. Most of these are screenshots, but you just have to follow along. Now, it does say complete the table of values, and we could do that, but we've actually got a spreadsheet which has done that anyway. Now, we've got to complete the table of values and sketch a bar chart of the sample distribution of p hat, given the population proportion p is equal to 0.2 and sample size is n equals 8. Okay, so how are we going to do that? Well, just remember your formulas for binomial distribution. Probability that x equals r is NCR p to the r1 minus p to the n minus r. We're going to put that formula into the spreadsheet, right, for different values of r in this case. All right, sample size is 8. Right, so our n value is 8 in this case. All right, and r is going to change values. Okay. Now, putting that formula into, here it is, putting that formula into the spreadsheet. right, we can generate what we need. Okay, so here are my values highlighted there. If we graph the probability of x equal to r, so this graph here is the probability of x equal to r. So just write that down. Okay, so the probability of x is equal to r. Okay, so if we're looking at 1, that's 0.3 approximately. And you can see what has happened here, how the values have been graphed there. Well, if you look at 1, this is a screenshot from the textbook. 1 corresponds to 0.3. Okay, so and they've gone up to. Okay, I can see what's happened. The values are not quite correct there, but we're not so interested in worried about the mistakes in the textbook. We're more worried about the shape of the distribution here. Okay, so if you look at our R values here, right, you're starting at 1. Okay, 0.33 goes up to there. Yep, 0.29. So we're more interested in the shape here. That's the most important thing. So let's move along to net, and here's some instructions here on how to do that on the spreadsheet. Okay, some more instructions there. Now, if you draw a bar chart for p equals 0.3 and n equals 10, using that previous formula from the spreadsheet, now we're just going to put these 3 solutions into the spreadsheet. Now, let's have a look at the shape of the distribution. Okay, you should see a progression. The bigger the sample size, so you can see we've got a sample size of n equals 10. The bigger the sample size, now you can see this is starting to look more like a normal distribution, can't you? Okay, so, and looking at the sample size of 50, you can see that the distribution really starts to look symmetrical, like a normal distribution. So we're not so interested in the numbers here, more so interested in the pattern of the distribution. So this is what we're looking at. We're looking at the bell curve, which is the normal distribution. So as samples become larger, notice that the sampling distributions become closer to the normal distribution. So you can see by the time we got to a big sample, we've got a nice symmetrical bell-shaped curve there. Now, this is called the central limit theorem. So the central limit theorem basically states for large sample sizes, the sampling distribution of p hat is approximately normally distributed. Right? This means we can use the normal distribution for discrete data with a large sample size. Now that's important because that means we can use the table of with the z-scores and the probabilities in that table to work out probabilities for discrete distributions. So in other words, we can approximate the discrete distribution with a continuous one, and therefore we can use the z-score table. Now, a couple of results we need to prove, and we're going to be using in the subsequent questions. Now, first one is E of p hat. Now, remember what these symbols stand for. So, the P with a hat is the sample proportion and population proportion. Okay, so just going back to the very beginning, just to remind you where those things came from. We go back to the beginning. My scrolling's not working here. It's better. All right, so going back to the very beginning when we defined, I'll scroll, that's better. Okay, that's better. Okay, so here is our sample proportion. Okay, sample proportion. And here's our population proportion P, which is also the probability of success P. So let's just go back to result here. Now, back on page 63, or 683 here, should I say, back on page 683, just to remind you, we proved this result. So page 683, we proved that the expected value, right, for the binomial random variable x is NP. Okay, now what we're going to prove is this result here. We want to prove this. Okay. Now, we know the formula for sample proportion. Here it is, x over n. That's what we've got to figure out. Now, this is 1 over n times by e over x. Okay, now, that's 1 over n times by, well, previously we proved that the expected value of x is np. That cancels with that, and we get p. So we just proved that the expected value of sample proportion there is equal to p. Okay, now, how does this work out? How do we do this step here? Okay, well, as an explanation, which is not in your textbook, we know that the expected value is equal to sum of all the x's and p of x's multiplied together. Okay, so if you're looking at the expected value of x on n, okay, that's the sum of all the x on n's times the probability of x on n, if you like. Now, okay, now we can write that as 1 on n, taking that out, x. Now, probability of x on n is the same as probability of x, so that is 1 on n. One on n times the expected value of x. Done. Okay, now, next formula we need. So this here is the first formula we're going to use in one of our questions. This is the second one. So this is our last new formula. All right, the variance of the sample proportion is P times 1 minus P over N. Now, to prove this formula, we need to remember a formula we did from that we proved previously on page 683 again. So in the proof, we're going to use this result which we previously have proved. Okay, now variance of the sample proportion is the variance of x on n. That's the definition of sample proportion. Now, the next step is to write this down as 1 on n squared variance of x. Now we're going to use that formula that we just underlined, and that's going to give me equal to 1 on n squared. Okay, variance of x is n p 1 minus p. So cross that out, and we get p outside of 1 minus p all divided by n. Okay, so that formula is proven. Probably wondering how this occurred. Okay, so to understand that, we've got to think about the definition of variance. Okay, so variance, which we've done before, variance of your random variable x is sigma x minus that squared times p of x. Okay, now if we're looking at the variance of x on n, so that's that. Now that's going to be x on n here. Now, if I've got all these x on n's floating around, that the average is now going to be that squared, and then probability of x on n. Okay, now without doing too much thinking, you can probably figure out then that this is sigma x minus that all squared and all divided by n squared, and probability of x on n, the probability will be the same as the probability of x. Okay, so then that's equal to 1 on n squared sigma x minus the mean squared p of x, which is just 1 on n squared times variance of x. Okay, that's done. All right, so make sure that all that's copied down. Let's do some questions. We're going to be using those two formulas now that we just proved. Okay, so let's have a look. We've got to... All right, so we're going to find the mean, variance, and standard deviation. Let's start off with the mean. Well, we know that the expected value is the mean, and we know that for the sampling distribution, all right, E of x is equal to P, right? And we're already given what P is in the question, it's 0.4. There we go. Now, the variance of x for our sampling distribution is P, 1 minus P, all divided by N. Okay, they give you what P is, it's 0.4. So it's going to be 0.4 times by 0.6 divided by your sample size, which is 50. And that's going to give you, work that into your calculator, and you should get 0.048. All right, don't forget this is a 0 here, not a 6. Okay. Now, standard deviation. Well, one thing you know about variance is the standard deviation squared. So that's the standard deviation squared. So that means the standard deviation will be the square root of that number, 0.048, which is equal to 0.0693. To 3 significant figures. So put that approximation there. All right, so that's my mean, variance, and standard deviation. Now, the other question, you can pause the video now if you want to have a go at the next question. It's exactly the same working out. So you're going to start with, where's my pen gone? Here we go. You're going to start with expected value of x, okay, which we know is the mean, which we know is equal to P for the sampling distribution, that is, and that's going to be 0.9. Now, the variance, again using exactly the same formula as before, P 1 minus P divided by N, which is 0.9 times 0.1 divided by 125. Now, plug that into your calculator and you will get 0.0072. Okay, now that's the variance of standard deviation. Well, we know that variance is standard deviation squared, so the standard deviation will be the square root of that, which equals 0.0268. 0.0268. Okay. Make sure that's copied down. We'll look at our last example for the course. Okay, so we've got the incidence of asthma in a particular population is 21%. A sample of 89 people was taken from this population. How many people in this sample would you expect to have asthma? Well, pretty straightforward, but we need this information for a later question. That's why they're asking it. So you're just going to find 21% of 89. All right, now you should get 18.69. Which will round up to 19 people, approximately. Okay. All right, now find the sample proportion as a fraction. Now just remember what the formula is. X divided by N. Now our sample proportion will be, the value of the random variable is 19, okay, and 89. There's our, because 89 is our sample size. Now, we will need that information a bit later. Now, let's have a look at part B. It says, assuming that sample proportion is approximately normally distributed, okay, what is the probability that the percentage of people with asthma, okay, so this should be a little typo here. You can just see that. That should be the word in. In a sample is less than 10%. Okay, so what we want to work out, so our random variable is X. Probability that X is less than or equal to 10%. Okay, now it says assume that we've got a normal distribution. Now we do have a table of values for the standardized normal distribution, which means Z scores. We need to convert the X random variable to a Z score. So that's what we're going to do first. So for our solution, okay, we need to work out our Z score. So that's going to be 10%, okay, 10% minus the mean. We'll take the mean as 21%, divided by the standard deviation. Okay, now, what is the standard deviation? Well, we need to work that out. But we already know how to do that because we have a formula for variance. The variance is the standard deviation squared. So the variance of P hat okay, so let's look at the variance. Well, the variance will be the standard deviation squared. Okay, so let's work that out. So variance of our random variable will be P, 1 minus P divided by N. Now, let's just have a look at that because I'm just going to rub something out here. Okay, that should be different. It should be P hat there. Right, so remember, here we go. So that's our formula. Now, they actually do give you enough information here because we know that the probability here of success, if you like, is it's going to be 0.21 there. And the mean is that as well. So you're going to get 0.21, okay, times by 0.79 divided by your sample size. Now your sample size is 89. Okay, and that is going to be, when you work it out on a calculator, 0.04317. Now, we need the standard deviation. Now, we know that the standard deviation squared is 0.04317. So we just have to take the square root of that to get the standard deviation. Okay, so it's going to give you approximately so look, so 0.21 times 0.79 divided by 89. Okay, that's my bad there. And squared there. I jumped ahead with my calculations. So with my calculations there, that's not quite right. That should be approximately 0.00186, and it keeps going. Okay, so let's just cross this out for a minute. It should be 0.00186, and let's just rub this out. That should also be the square root of 0.00186, which when you square root that gives you 0.04317. Okay, so there's our standard deviation, and now our z-score can be completed. So our z-score will, just write this underneath. For the z-score, we're going to have z is equal to 10% minus 21%. Okay, all divided by the standard deviation, 0.04317. Now that should give you negative 2.55. So with your standard deviation now, there's your bell curve. You know that in the middle there you've got a z-score of 0. Now, 2.55 will be over here somewhere, and negative 2.55 would be here. So you've got to work out now the probability. You want, well, let's have a look. So the probability that x is less than or equal to 10% is equal to the probability that z is less than or equal to negative 2.55. Now, this is the area that you want here. But this area is also the same, just here. Now, I'm going to use the positive value because a lot of the tables only give you positive, even though your textbook has the positive and negative values. So we're going to go 1 minus the probability Z less than or equal to 2.55. Now, if we go to our table, okay, which is just here. Now, 2.55, I've got it highlighted in green there. There's 2.5, and you can see that this corresponds to the second decimal place of 5. So I come down there, and that is 0.9946. Okay, so that means over here, I've got 0.9946, which gives me my final answer of 0.0054. Okay, so the probability of less than or equal to 10% or less than 10% is 0.0054. Now, it did say less than 10%, but we know for a continuous random variable, it's the same. So I can just write this down. That's my answer. Okay. Now, part 2, that's going to be very similar. Let's do that in a different color. It'll be very similar to the working out, but it'll be less working out for us. So for part 2, okay, now remember the Z-score formula. We will need that. So we've got to work out the probability that the X random variable is bigger than 30%. Now, so we can use the table, we need to create a Z-score. The Z-score will be 30% minus 21%, which is the mean. Okay, divided by the standard deviation. Now, we just worked out the standard deviation, so I'm not going to do that again. 0.04317. Now, you should get 2.08. All right. So just draw a little picture of what you need to find. Now we are looking at, well, we've got to work out the probability that Z is bigger than 2.08 for the Z distribution. Okay, here it is. Now, there's Z equals 0, so 2.08 is over here. We want this region here. Okay. So to get that region, we're going to do the same thing as before, and that is we are going to say that the probability will be, let's just write down, equals 1 minus the probability that is Z less than 2.08. Okay, so we've got to go back to our table, find 2.08. So 2.08, I've got it highlighted. So there's 2.0. And then this is the 8 column for the second decimal place. So it's 0.9812. So let's write that down. 0.9812, which equals 0.0188. Okay, so that's the last answer. Now, that is all we've got to write down, and make sure all that's copied down. And that's the end of the lesson.